है भाई।
स्टार्ट।
स्टार्ट हुआ। हम्म। है कोई नॉट इट। नो रिस्पॉन्स। कोई है ही नहीं।
वेटिंग में सर, आप डेली तो क्वेश्चन
हाँ। हेलो, गुड आफ्टरनून। Welcome you all to second live session on advanced transcendental chemistry. And it was announced almost a week back. Unfortunately, you people didn't pose any questions. You didn't send any questions. Doesn't matter. If you have questions, let's start discussing without wasting our time. Okay, why don't you write your question on chart so that we can start discussing. I hope you're all enjoying uh, this course. First of all, those who are present, please write your name. So, no matter how good or bad the question is, do not hesitate to talk to me. Those who are present, please write your name. And then start writing your question. Hmm? Hmm. Okay. Okay. Not this one. Hmm. So participants are yet to come. There are six people. Okay. Six people mostly. We have to wait for a few more minutes. Those who have come for this live session, please write down your name and introduce yourself by writing what you are studying and from where you have come, which college you are studying. So that's good enough. From the moon, right? Any question? How does the
breakdown?
I don't know from where he got. I didn't discuss about this one. Von Oppenheimer approximation. I didn't discuss that. I didn't discuss it all here. So in what context you are asking that question about von Oppenheimer approximation? Of course, you are talking about uh, you know modeling exercise dynamics. Okay, so that's I don't think that's beyond the scope of this lecture. Yes, that's what it's. Yeah. So this he should refer to. Okay. As something that is quite relevant to this, okay, what I have taught in this course. Okay. Hi, Arav. Welcome. Yeah, well, that's an interesting question. Your question I read out. Uh, why does spin orbit coupling in 4D and 5D transitional metals drastically alter magnetic and spectroscopic properties, and how do relativistic corrections quantitatively affect optical orbital splitting? Yes, if you just look into 3D, 4D, and 5D, okay, again, if you look into the crystal field stabilization energy, that drastically increases from 3D to 4D to 5D, okay? And one more thing is, and the orbitals also, orbital size also increases. When the orbital size increases, okay, there is a possibility of energy difference also considerably decreases, okay, uh, within the principal number or the next one, okay, principal quantum number. At that stage, what happens? There is a possibility of diffusion of orbitals. Okay, when the diffusion of orbitals are there, okay, so naturally your spin orbital coupling will be quite affected. Normally, you don't see spin orbital coupling in case of 3D. Invariably, you don't see it at all. Okay, unless there are few cases we come across. In general, we don't see spin orbital coupling among 3D, but that's in case of 4D and 5D. It does show considerably. This has to do with crystal field stabilization energy, and also if you go with ligand field theory or molecular orbital theory, how these energy levels are situated, okay, and what is the gap between HOMO and LUMO, and all these things comes into the picture. When you talk about relativistic corrections, okay, so that can be done. Uh, But first of all, you should know what is relativistic corrections. Okay, relativistic effect, you should know what actually happens and how the electrons are rotating, what is the speed of electrons, and all those things are needed. Okay, to understand that one. But one thing what you should remember is uh, the spin orbital coupling is quite remarkable in case of 4D and 5D compared to 3D, and also it is also quite well pronounced in case of lanthanides and actinides as well. And also we have a thumb rule. By simply looking into the electronic configuration, we should be able to tell whether spin orbital coupling occurs or not. Okay. But however, uh, that is not really applicable in case of 3D. Okay. Once you start placing the electrons using even crystal field or ligand field energy levels, you should be able to look into it, and you should be able to tell, okay, under what conditions spin orbital coupling occurs and what condition it doesn't affect. But nevertheless, okay, in 3D it is less pronounced. You have any other question? Yeah, I'm just waiting for your questions. May I know who are all present now? Can you just write down your name? Ronik, you have a question? Ronak? You have any queries about assignment? The last assignment? And what are your opinion about assignment questions? Are they difficult, easy, or you want a different type of assignment questions? Since a particular assignment revolves around whatever the lectures that are given in that week, okay, we try to restrict to only those five lectures. As a result, there can be some repetition of the similar questions. What is the meaning of medium question paper? You mean questions are moderate? Yeah, someone is saying hello. Yes, you have a question? You should come prepared to ask some questions, or since it will be announced well in advance, you should write to us what questions you have in your mind. And also, if you haven't understood a particular topic, you have to tell in well in advance so that I can bring those lectures and I can, spend some valuable time discussing those things with you. And if you come here and start looking into the questions, that's a problem. So your Ankush Sharma, why do transient metals show colors in compounds? Well, why they show? It's because of electronic transitions, right? So for electronic transition, what they do is they absorb a particular wavelength in the visible light. If they are okay, and then when the electrons are coming back, they emit that one. So the basically what happens, whatever the energy they consume, okay, complementary color will be, you can see as a color of that compound. Okay, it's basically they absorb, okay, wavelength, a particular wavelength of visible light, and as a result they appear. Okay, but if you take those compounds, no matter how intense they are in color, if you take them into the dark, they will not be colored. Okay, so color comes only when they absorb the light. Okay, and depending upon what wavelength they absorb, they exhibit the corresponding complementary color. Have you ever checked taking a red compound into a dark room and see how it looks like? Whatever the substance we see colored, all have similar properties, absorbing a particular wavelength of visible light and then appear the complementary color. Well, when we are doing catalytic reactions, okay, catalytic reactions are most of the time, okay, it's a redox process. Initially, what happens when you take electronically unsaturated and coordinatively unsaturated metal complex, okay, and you take a substrate will be added oxidatively. At that stage, what happens? Oxidation state increases by two numbers and coordination number increases by two numbers, right? So, and then uh, at the end, what happens? The coupling or whatever happens, and then reductive elimination takes place. Then, how to identify? Yes, for identifying, you have spectroscopic methods are there. For example, if you look into various oxygen states, they have very characteristic absorptions are there in the electronic spectroscopy. So, you should go for UV visible spectroscopy, and also in some cases, what happens? A diamagnetic compound can become paramagnetic so that NMR doesn't hold, or EPR you can use. So spectroscopic methods can be conveniently used to look into the right oxidation state of a particular intermediate in a catalytic reaction. How do transmetals exhibit magnetic properties? Transmetals have lone pairs. Those uh, which have lone pairs, okay, these electrons also act like a tiny magnets, right? So that's very fundamental question. Okay, so transition metals, if you take anything, even oxygen, okay, oxygen O2 is paramagnetic because these two unpaired electrons are there. And if you liquefy uh, oxygen and make it liquid oxygen, that looks blue in color because of two unpaired electrons. Okay, so magnetic properties are there. You can measure the magnetic properties by using magnetic susceptibility instrument, and why they exhibit is because of unpaired electrons. So magnetic moment also increases with more number of unpaired electrons. Yes, Harshit, you have a question? What does it mean? What if perpendicular? What question you are asking? What makes a metal a transition metal? You're already telling what makes metal a transition metal. Okay. Why we call it transition? Okay. Why we call them transition metals? They have the properties between S block and P block. Okay. And the properties are very different from main group and then P block elements. Okay. And that's the reason we call them as transition metals. Okay. And also when you go for post transition metals, we call them. Okay. If you go for F block elements. If a metal has unpaired electrons in the d orbitals, or if you start filling the d orbital, then we call them as transition metals. That is, okay, divided into three groups, 3D, 4D, and 5D. And of course, post transition metals we call 4F and 5F block elements, where we come across unpaired electrons in F orbitals. All transition elements have, okay, unpaired electrons in their d orbitals. Okay, the number of electrons can vary from 1 to 9. The moment it becomes 10, like zinc, cadmium, and mercury, where we have N210, NS2, okay, so they are not transition elements. So neither they are transition elements nor main group elements, but nevertheless, they exhibit properties of both. And if you just look into them, they look very similar to alkaline earth metals. Yeah, well, the shielding effect is minimum in case of lanthanides. The reason is very simple. Okay, Um, the inner electrons, okay, miserably, less impactful in preventing the valence electrons in having nuclear influence. Okay, the reason is very simple. Effective nuclear charge is increasing and size is not increasing. As a result, there is not much change in the distance between the nucleus and the valence electrons in case of lanthanides. As a result, what happens? The shielding effect is minimum or similar to what we come across in case of 3D, 4D, and 5D elements. There is some shielding, but it doesn't affect or increase, because every time when you say an electron is moving away, you see nuclear charge is also increasing. Okay, because electrons are added to the same subshell. As a result, screening will be minimum. Because if the screening is there, and effective nuclear charge is also increasing, that nullifies, okay, throughout lanthanides, and because of number of electrons present and mostly the stronger nuclear forces. So you don't see much uh, shielding comes, screening is less. Okay, that's the reason the contribution of shielding is very minimum in case of lanthanides. That we call it as lanthanide contraction. If the shielding is minimum and the effective nuclear charge is increasing with increase, when you add an electron, you're adding a proton as well. Okay, as a result, what happens? Steadily, okay, if nuclear charge is increasing because of addition of a proton and the size is not increasing. As a result, what happens? Whatever the outer electrons are there, they are pulled more towards the nucleus. As a result, shielding remains same. Of course, shielding, you can also calculate this, okay? Uh, Shielding for a particular electron in a valence orbital, you can calculate. Okay, can we use the time-dependent Schrodinger equation to model non-adiabatic transition between DD excited states in a transmetal complex? Yeah, you better ask a quantum chemistry person. He can give you a better suggestion about that one. For that question, better you ask a quantum chemistry person. He can give you better answer. You see, there are some quantum chemistry courses on NPTEL. Okay, what you do is just go through that. Probably there may be some, somewhere they discuss some of those things. I'm not sure about that one. Okay, because this is a very a special particular question you're asking, so that probably he may or may not discuss those things. Okay, my suggestion would be to look into Shriver and Atkins' book. No, not Shriver and Atkins. Atkins' physical chemistry book, you just look into it. Probably there may be some information. Okay, let me look into, okay, some books. If any information is there, I shall pass it on to you. Okay, just send an email to me. Yeah, you see, that's an interesting question. Why transition metals exhibit highest tungsten states in oxides and fluorides? If you just look into the periodic table and if you look into the periodic properties of fluorine and oxygen, the highest electronegativity is shown by fluorine. The next one is oxygen. They are so strong. Okay, if any element in the periodic table exhibits highest possible oxygen state, there has to be a strong electronegative element should be attached to it. They are oxygen or fluorine. Okay, that is the reason. So being most electronegative in nature, oxygen and fluorine are capable of taking out all the electrons from the metal to make it exist at its highest possible oxygen state. Okay. So it has to do with electronegativity of those elements. Okay, if there is an element, okay, if from which you can take out all the electrons, you have to use either fluorine or oxygen. Mostly it is fluorine. For example, if you take platinum you can take out 6 electrons. Okay, chromium you can take 6 electrons. Iron you can take 8 electrons. Okay, and rhenium you can take 7 electrons. So that means basically when you say all the electrons, d electrons and s electrons, nd and n plus 1 s electrons have been taken away, it has to be uh, with it has to be an oxide or a fluoride. It's That is a property. I mean, they can even, you know that even inert gas elements, okay, krypton and xenon, you can also take away electrons from them, okay, when they are reacting with oxygen or fluorine, okay. It's because of electronegativity of those elements. They can oxidize any element in the periodic table. Why does the enthalpy of atomization of transition metals remain high compared to main group elements? So here, okay, enthalpy of atomization means it's basically breaking the metal-metal bond. Okay, so you know that if you look into main group elements, okay, you don't come across metal-metal bonds. Of course, metalloids are there. Okay, partly metallic properties increases down the group among main group elements also, and also we come across metal-metal bond in case of alkali metals, that is bare minimum. Okay, so there you don't have many electrons, whereas here in case of transition metals, because of extensive metal-metal bonding, atomization is not easy, and hence they exhibit higher melting point. Okay. And it appears like a positive cations are there with a layer of electrons moving on the surface. It appears something like that in case of transition metals. Okay, you have a steady flow of electrons on the surface of the metals. So that holds the two atoms, okay, together. And as a result, what happens? There is an extension of metal-metal bonding. Okay. Okay. Well, disproportionation. Okay, in disproportionation, what happens? For example, if you take a palladium 2 compound, okay, if I say it undergoes disproportionation, it forms palladium palladium 2 compound. If you take, it becomes palladium 1 and palladium 0. Okay, so that means one will be reduced, one is oxidized. So that is called disproportionation reaction. You take a metal complex, and if you say our metal complex or anything that undergoes disproportionation, means basically you have two entities, one loses electron, one gains electron. Okay, that's called disproportionation reaction. On the other hand, if you take one lower in oxidation state, one higher in oxidation state, and bring them together, and you get a product that's called conproportionation reaction. So that means a disproportionate reaction, when it comes back, okay, backward reaction is conproportionation reaction. Okay. You take, is that clear? Then the term itself is self-explanatory. Disproportionation. Okay, that's what exactly happens. Any other question? So as a part of this course, you think anything else should be something other than what is there should be discussed or it should be included? Then can you tell me what are the other topics you think that should be included in this course? Any other question? In case if you come across any question, you please mail it to me. I shall try to answer. Okay. I will give you a few more couple of. Not the lowest oxide of transition metal is basic and the highest is amphoteric. So the lowest state of transition metal is basic means it can readily give electrons. Okay, so that's the reason it's basic. And the highest is amphoteric, not necessarily all the time. Only few are amphoteric in nature. Okay. That is very specific. Not all can be amphoteric, but nevertheless, the lowest tax state. Okay, if you take a metal in the lowest tax state, it's basic because it has more electrons in it. Okay, and that can be readily donated. Okay, so if you just compare that one to Lewis acid base properties, okay, it becomes very clear. And the highest oxidation state, they will be highly acidic. Okay, they will be reducing in nature. Okay, oxidizing, reducing in nature. So oxidizing in nature, they can be get readily reduced. Okay, so when they are looking for electrons, they will be possessing acidic property. When they have excess electron that can be donated, they will be having basic properties in nature. For example, if you take um, copper 1, okay, and copper 2. And also, you can also compare with hard acid and hard base and soft acid and soft base also. Uh, Metals, they in their highest tungsten states are hard, and mostly anionic ligands are hard. So hard compounds are more stable. And soft are more stable. Copper 1 with soft ligands like sulfur or phosphorus. Okay, they are more stable. And also that also you can see in nature in what form they exist, in the form of oxide, sulfide, or halide. That also depends on what kind of properties they have, whether they are hard acids or hard base or soft acids or soft base. Okay. Yeah. Here is the email. Okay. First, try to read, okay, yourself and try to understand. And if you do not understand, then write to me. Because when you are reading yourself, you will learn more than what you are looking for. So cultivate the habit of reading textbooks. That helps a lot. Any more questions? If not, I will wind it up. So look into worked examples that I have solved in these lectures. And also what you should do is look into Inorganic Chemistry by Shriver and Atkins book, an excellent book. And another book is by C.S. Housecraft. Okay. So all chapters have very interesting and useful questions are there. If you solve all of them and also look into worked examples, you should be able to understand in a better way. Okay. Please do that one. Okay. If you are taking competitive exams, better to solve those exercise questions present at the end of each chapter in those two books. Very, very good questions are there, very useful questions are there. And once you solve those questions, okay, there's no need to remember anything as far as inorganic chemistry is concerned. Please do that. So if there are no more questions, so I will try to wind it up this live session. Okay. And if you have more questions, okay, possibly I will take one more live session sometime in October. That depends on okay uh, uh, your requirements. Okay, if you need, then what I should say is ask those questions or some topic which you haven't understood, you want that to be little bit more elaborated, please send questions. Okay, then we can plan for another live session sometime in the uh, end of September or first week of October. Okay. So enjoy reading. Okay, so thank you.